Okay, so 9, 15, 14, this is where we left our chemistry heroes, and we're going to add some things to what you were responsible for over the summer. Those were mega and kilo, centi and milli, and now to that we are adding micro, nano, and pico. And you're responsible for knowing the powers of 10 that go with those. Okay, great. Got this weird sort of box there. We'll talk about that in a second. So we had talked about derived units. These prefixes can be used to modify any SI or any metric unit, and they each have a power of 10 associated with them. So mega is 10 to the 6th, kilo is 10 to the 3rd, centi is 10 to the -2nd. You guys have the book right out, huh? Not that you wouldn't have known it off the top of your heads. Milli, 10 to the -3rd. Micro, the weird one, -6. Nano, 10 to the -9th. And pico, 10 to the -12th. So once you get past centi, they're all multiples of 3. 3, 6, 9, 12. So if you can remember them in order. Now, this weird sort of bar here, that's the just 1. And this is the metric base units. So in the video over the summer, we talked about metric system versus SI system. And the SI system is a very specific, very narrow subset of all metric measurement. There are things that are metric that aren't SI. So when we talk about SI base units, the SI base unit for mass is the kilogram. For length is the meter. But when we're doing conversions, we're talking about more of a metric base unit, and we want to use the things that do not have a prefix. So meter, liter, gram is very often how that's remembered. We use liters in chemistry, but do you remember from the summer video, is a liter an SI unit? It's not. The SI unit for volume is the cubic meter. So volume SI unit, cubic meter. We very often use the liter, and we use that very often here in chemistry. That's going to become important. I'll tell you a little bit about the sneakiness of that in a second. Okay, so we've got all these prefixes we can use to modify things. We can make derived units, such as the cubic meter. Let's talk a little bit more. Well, let's take one sidebar real quickly. Cubic meter is the SI unit. It's a derived unit, but SI derived unit for volume. It's made up of other SI units. This liter that you speak of. So here's how you get from SI into liters, vice versa. We have this relationship. 1 milliliter is equal to 1 cubic centimeter. So you've got your graduated cylinder over there. In that graduated cylinder, if you have 1 milliliter of water, that would fill up a cube that's 1 centimeter per edge. So they're equal amounts, and you'll use that conversion. And I'll throw you a couple of those. So that one's important to know. So all conversions are based on using a conversion factor of some sort, and it's a way to get from one set of units to another. And all conversion factors is multiplying by 1. That's all they are. Can you multiply something by 1 and not change what you were originally given? Yeah. You can multiply something by 1 500 times. You're still going to have whatever it is that you were given. All a conversion factor is, it's something where the thing on top is equal to the thing on bottom. That's all it is, at its most simple. If the two things are equal to one another, guess what this really is? It's 1. When you have things that are equal, top and bottom on a fraction, that's the same as multiplying by 1. So, and I don't even like that slide anymore. I need to get rid of it. But, oops. So remember algebraically that x over 1 equals x, but 4 over 4 equals 1. That's all we're saying here, is if we have two things that are equal, top and bottom, they're equal to 1, and you can multiply by 1 forever and not change what you were given. Now, the method that we use to do conversions in chemistry is factor label. And again, if you had some people for physical science who did lots of factor label, you may not have if you had other folks, but you'll be good at it by this time next week. Okay, so since not everybody had a really solid grounding in factor label, let me give you the overview. Factor labels are just repeated multiplication and division, and they are typically set up like this. So we make this little sort of hash grid, and we put things on the top and bottom, and we multiply and divide. So it's beautiful and simple in that we can put a bunch of stuff here, and that is equal to x times y times z divided by a times b times c. Okay? It couldn't be a whole lot easier. When you combine that with doing the scientific notation stuff, it's actually really kind of pretty. So that's all you're doing. Anything that's side by side, you multiply top and bottom, you divide, and your best bet is to get everything multiplied and then divide the top by the bottom. So, okay. Let's practice a conversion. Okay, 374 micrograms. We want to know how many milligrams this is. Now, you did these on the tutorial over the summer. So the first thing to know is that whatever you're given is always going to go in your first box. So this is 374 micrograms in your first box. And I always stick a 1 underneath that so I don't do anything stupid. Because you don't want to put anything under that. That's sitting by itself. Now, the other thing that I do to make life easier, starting off, is I convert this to scientific notation right off the bat. 3.74 times 10 to the second micrograms. And that means, remember how I said I tend to screw up if I have to move decimals? If you do this initially, you don't usually have to move decimals, and it's one less place to do something dumb. So I'm a big proponent of limiting the number of places where you can make stupid mistakes. So I find that useful. Now, the next thing you got to know is that whatever units you have here are also going to go down here so that they all cancel. The other thing you need to know, that metric base unit idea. Every single square past your first one is going to have a relationship back to the metric base unit. So here, we're in micrograms. Our metric base unit's going to be grams. And even if you're going from milli to centi, doing it this way, you always go back through the base unit because those powers of 10 are all relationships back to the base. They're not to one another, they're back to the base. So you have to go through the base. It's not that hard. Okay, and then we know that units here are going to be the same as down here to cancel. And we know we want to end up in milligrams. So right now, if we just check our units, this is dimensional analysis. Micrograms cancels, grams cancels. We would end up in milligrams, and that's what we want. Perfect. So now we're going to plug in our relationships. Doing it this way using your powers of 10. This is so easy. Every place that you see something with a prefix, you put the number 1 immediately. If there's a prefix there, stick a number 1 in it so you don't do anything stupid. Your powers of 10 always go with your base. Always, 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 always go with your base. So, micrograms, the base is what? 1 times 10 to the -6, right. For milligrams, the base is 10 to the -3rd. Okay, now we've got our problem set up. We're ready to solve. Okay, 3.74 times 1 times 1 divided by 1 times 1 times 1 times 10 to the 2 plus -6 minus -3. Huh? Okay, all I did was I pulled these ones out of that problem and I put them down here. You don't have to do that, obviously. I do it just to show you where everything's coming from so you see where it's coming from. I don't expect that any of you will do that later on. But doing this is useful because you've got a lot to track here. So 2 plus -6, we got -4, and that's -4 plus 3, So this is all -1. So what we have for an answer is 3.74 times 10 to the -1st micrograms. Or milligrams. Good grief, sorry. Okay, 3.74 times 10 to the -1st milligrams. Easy to do if you remember the rules. Check your units. Remember your powers. Don't screw those up. I'm going to do one more together, and I'm going to turn you loose on a practice sheet. Okay. Okay, we have 47.9 kilograms equals how many micrograms? First box is always your given. And I want to put that in scientific notation just to keep my life simpler. I know that kilograms has to go in the next box and down below to cancel. And I know that I have to go through the base unit. So that's going to be grams. What's going to go on the bottom in that last box? Grams to cancel. And up here we're going to use the one that we want to end up in. So this will be micrograms. Check your units. Do they cancel? Yep, they do. We end up in micrograms. Let's stick our ones in where we have prefixes so we don't have a chance to do something dumb. What's the power of 10 associated with kilo? 10 to the third. And the power of 10 associated with micro? Yep. Now what did I just do? I put those in without the 1 times. Can you do that? You can. It doesn't matter, and it, for some people it simplifies the bookkeeping. So now we have 4.79 times 1 over 1. Whoops. Whoops. Sorry. Times 10 to the 1 plus 3 minus -6. So 4 plus 6, 10 to the 10th. Okay, so our answer is 4.79 times 10 to the 10th. Everybody comfortable with that? Okay. I'm going to give you a practice sheet. I've added a couple additional problems in the book review that are related to this material. And the rest of the time is yours to work, ask questions, and the practice sheet key will be in the hall. So the question was, do you add or subtract the exponents? So the 10 to the first, we're multiplying with this 10 to the third. So those are added. This 10 to the -6th, we're dividing. So we're subtracting. And I tend to, because it's very easy to screw up subtracting negatives and adding negatives and positives, so I will write plus a negative, minus a positive, minus a negative, and then correct myself, because otherwise I tend to screw it up. Let's do one just to demonstrate that idea. Okay, so we've got another one. 2.5 times 10 to the -4th. I already have it in scientific notation. Megagrams, grams, milligrams. Okay, shoop, shoop. And 10 to the 6th and 10 to the -3rd. So it's going to look like this. 2.5, and we'll just leave that alone, times 10 to the. So first we're taking this, -4th, plus this, minus this. Well, it's a -3. So we're going to end up adding it, but I have a hard time keeping track of those, so I strongly recommend doing that, where you write minus a negative, because then you're going to look at that and go, oh, okay, well, that's really +3. But I tend to not change them until I've gotten them written. I find that that's a really common source of error on student tests and in student work, which is why I recommend doing it that way. So that would be, let's see, -4 plus 6, so that's 2, plus 3, so that's 10 to the 5th. Okay, that was just another example, but I forgot to record, so,